Welcome back to the Deep Dive, where we plunge into the cutting edge of AI and machine learning. Today, we're diving into something truly remarkable, the incredible pace of large language model evolution. These models are no longer just vast knowledge repositories, they're rapidly becoming active problem solvers, capable of tackling complex, real-world challenges. It's a significant leap toward the ambitious goal of artificial general intelligence, highlighting how these systems are truly transforming into powerful generalists.
Indeed, the shift is profound. We're moving beyond models that merely know things to models that can do things, interact, reason, and create in ways that were, well, previously fragmented across different systems or simply beyond the capabilities of a single AI. This is where the rubber meets the road for real-world productivity, and where we begin to see these models augment human capabilities in tangible ways.
And at the forefront of this transformative shift is the GLM-4.5 series from Zhipu AI and Tsinghua University. This is a monumental open-source development, making cutting-edge AI accessible to a wider community. Our mission today is to cut through the complexity of their extensive research paper. We're going to extract the most important technical details, the surprising findings, and the core insights about GLM 4.5, giving you a comprehensive understanding of what truly makes this model stand out. Our focus is purely on the technical advancements and their deep implications for the field of AI and machine learning.
Exactly. We'll be unraveling the intricacies of its novel architecture, its sophisticated multi-stage training process, and how its remarkable performance is meticulously evaluated. For you, whether you're a seasoned developer, a budding researcher, or just intensely curious about the technical frontier of AI, understanding GLM 4.5 offers invaluable insights into the architectures and training methodologies that are driving cutting-edge performance in large language models. Think of this deep dive as your shortcut to being well-informed about one of the most significant open-source LLM breakthroughs we've seen recently.
Okay, let's unpack this. For years, we've witnessed LLMs evolve from sophisticated text generators to general knowledge repositories, essentially digital libraries with incredible recall. But now, the fundamental focus has profoundly shifted towards making them general problem solvers. What does that truly entail? It's about developing models with human-level cognitive capabilities across diverse domains, aiming for that unified mastery of complex problem-solving, generalization, and self-improvement. It's not just a stepping stone. It feels like a stride towards artificial general intelligence.
It's the critical difference, isn't it, between an AI that can tell you about how to fix a complex software bug and one that can actually identify and fix the bug within a real code base, interacting with development tools. The GLM 4.5 paper identifies three critical interconnected capabilities that they use to measure a truly generalist model, often referred to as ARC. First, we have agentic abilities. This isn't just about answering questions from stored knowledge. It's about the model's capacity to interact autonomously with external tools and the real world. Think of it navigating a website to find specific information, using an API to book a flight, or even interacting with a simulated operating system.
Right, like browsing the web to research a topic or connecting to a flight booking system to find the best deal. That's a huge leap from merely generating static text. And second, we have complex reasoning. This goes far beyond simple question answering or recalling facts. We're talking about solving multi-step problems in highly structured domains, like advanced mathematics, intricate scientific puzzles, or even logical deduction challenges. It demands deep, multi-step thought processes.
And finally, advanced coding skills. This isn't just about generating snippets of code in isolation. It's about tackling real-world software engineering tasks, debugging complex issues, understanding and modifying existing large code bases, and even generating robust unit tests. What's particularly fascinating here is that while proprietary models like OpenAI's GPT-4 Claude Opus have shown groundbreaking performance in specific ARC domains, achieving a single, powerful open-source model that truly excels across all three areas has been a significant and, well, elusive challenge until now.
And that's precisely where the GLM 4.5 series steps in. It's positioned as a major step towards unifying these disparate yet critical capabilities within an open-source framework. Let's talk technical specifications, because these numbers tell a powerful story about their approach to efficiency. GLM 4.5 is a mixture of experts, or MOE large language model. It boasts a staggering 355 billion total parameters, but here's the kicker. Only 32 billion activated parameters at any given moment.
Which is a huge difference. And for those needing a more compact solution, or for deployment scenarios where computational resources are tighter, they've also released GLM 4.5 Air. This is a smaller MOE model with 106 billion total parameters and an even leaner 12 billion activated parameters. This parameter efficiency is absolutely key for real-world adoption. What's particularly noteworthy, and something we'll definitely get into, is their hybrid reasoning method.
Uh-huh.
This model uniquely supports both a thinking mode and a direct response mode.
A thinking mode versus a direct response mode. That sounds revolutionary. Beyond just efficiency, what does this imply about the internal cognitive process of the model? Are we seeing early signs of metacognition, where the AI is actually evaluating its own task and deciding on the optimal approach? How does that contrast with models that might always try to generate a verbose chain of thought, even when unnecessary?
That's a perceptive question.
Exactly.
For complex reasoning or multi-step agentic tasks, the model can engage in this deliberative thinking mode, performing internal steps to arrive at a solution akin to a human explicitly thinking through a problem. But for simple chat or straightforward queries, it can intelligently bypass that multi-step process and offer an instant, direct response. This is a significant contrast to previous models that might either lack the internal mechanism to differentiate or might always generate a verbose chain of thought, even when a concise answer is all that's needed. This intelligent self-regulation of its own cognitive process makes it far more adaptable and efficient.
Right. So the immediate implication for you, the listener, is quite significant. GLM 4.5 achieves strong performance with significantly fewer activated parameters than several competitors. This means more efficient inference and potentially lower operational costs for deployment, which is a major win for the open source community, enabling broader access and experimentation.
Absolutely. It's getting more bang for your compute buck, and with a nuanced intelligence. Speaking of efficiency, let's delve into the architectural innovations that underpin this. They've chosen the mixture of experts, MoE architecture. Why MoE? What's the fundamental advantage here that makes it so compelling for models of this scale?
MoE is adopted precisely because it dramatically improves computational efficiency for both training and inference, especially for models with a massive total parameter count. Instead of activating all parameters for every single token, a MoE model intelligently routes each token through a small subset of specialized experts within the network. This means you can have a gargantuan model with hundreds of billions or even trillions of total parameters, but only a fraction of those parameters are active at any given moment. It's like having a vast library with every book imaginable, but you only pull out the specific 2 or 3 books you need for your research rather than trying to read the entire library for every query. This selective activation makes it far more efficient to train and run. So it's like having a giant team of specialists, but you only call on the 2 or 3 experts most relevant to the task at hand, rather than having the entire team weigh in on every single query. That makes a lot of sense for efficiency. Now, they also detail some specific MoE layer design choices, like loss-free balance routing and sigmoid gates for MoE layers. How do these specific components contribute to load balancing and the intelligent routing of information?
Loss-free balance routing, as the name suggests, aims to distribute the workload evenly across all experts without incurring an additional loss term in the training process. This is absolutely crucial because if some experts are consistently overloaded and others are underutilized, you lose the efficiency benefits of MoE. Imagine a busy restaurant kitchen with many specialized chefs, each an expert at certain dishes. Loss-free balance routing is like an intelligent order routing system that ensures every chef gets a fair, productive share of the incoming orders so no one is overwhelmed while others stand idle. You maintain peak efficiency without any extra cost from an imbalanced system.
Okay, that keeps things running smoothly. And the sigmoid gates.
As for the sigmoid gates, they contribute to the routing mechanism by determining which experts are activated for a given token. They essentially act as switches that, based on the input, decide which expert pathways the information should flow through. Think of a busy train station with many platforms, each leading to a different expert destination. The sigmoid gates are like the digital signalmen who, based on the incoming train's unique information, quickly decide which specific track it should take to reach the most appropriate platform efficiently, avoiding traffic jams and ensuring a smooth journey.
And here's where it gets really interesting and counterintuitive, the depth over width finding. They found that deeper models, meaning an increased number of layers, but with reduced width, like a smaller hidden dimension and fewer routed experts, exhibited better reasoning capacity. That seems to challenge some common LLM scaling intuitions where we often hear about simply increasing model width for more power.
It absolutely does challenge that conventional wisdom, which often leans towards wider models to increase raw capacity. However, this finding suggests that for certain cognitive abilities like complex reasoning, adding more sequential processing steps going deeper might be more effective than simply increasing the parallel capacity within each layer. Think of it like building a very deep, focused team where each member meticulously builds directly on the work of the last, rather than a wide team where everyone is working in parallel on different aspects. For truly complex, multi-step problems, sometimes that deeper, more sequential thought process is what wins, suggesting a fundamental rethink of how we design for advanced cognition in AI. This is a subtle but profound insight into model design for reasoning tasks.
That's a fascinating technical nuance. It suggests that architectural choices can be tailored not just for overall performance, but for very specific capabilities. So it's not just about giving the model more brain cells but about giving it a more sophisticated internal thought process, depth, when it comes to reasoning. This hints at a future where AI architects will be more like cognitive psychologists, mapping out specific thinking pathways rather than just scaling up raw compute. Let's move on to the self-attention component enhancements. They mention using grouped query attention with partial ROBI. What are these components and how do they contribute to improving attention efficiency or context handling?
Right, so grouped query attention, or GQA, is an optimization of the standard multi-head attention mechanism. It reduces the computational cost of inference by having multiple attention heads share the same key and value projections. This can significantly speed up inference without much performance degradation, especially for larger models. Partial rope, or rotary position embedding, is a method for encoding positional information within the attention mechanism. It allows the model to understand the relative positions of tokens in a sequence. By applying it partially, they likely found a sweet spot for incorporating positional awareness efficiently, especially for handling longer contexts, given that their models also support vastly extended sequence lengths.
They also increased the attention heads to 96 for a 5120 hidden dimension. And here's another counterintuitive observation from their paper. While this didn't directly improve training loss, it consistently improves performance on reasoning benchmarks, such as MMLU and BBH. How do we reconcile that? Training loss is usually the direct measure of how well the model is learning the data, so this seems to defy expectations.
It really does. This is a prime example of where direct training metrics don't always align perfectly with downstream task performance, particularly for complex capabilities like reasoning. An increased number of attention heads means the model can attend to a greater variety of patterns and relationships within the input sequence simultaneously. While this might not directly reduce the raw prediction error on the training data, perhaps because the core patterns are already learned, it could lead to a richer, more nuanced internal representation. This richer representation is then more effective for the intricate logical steps and multifaceted understanding required by reasoning benchmarks like MMLU and BBH. It's about building a better, more robust internal understanding of the world and problem structures, rather than just optimizing for next token prediction.
I see. So a richer internal state helps with the harder tasks, even if it doesn't lower the basic prediction error. And to stabilize this complex attention process, they incorporated QK norm.
Exactly. QK norm serves to stabilize the range of attention logits, preventing extreme values that can destabilize training. It keeps things in check.
So it's about making the attention mechanism more robust and informative, even if the raw loss doesn't reflect it directly. They also added a multi-token prediction, MTT layer, which is itself a MoE layer, to support speculative decoding during inference. How does this innovative addition speed up generation, especially for longer outputs?
Speculative decoding is a powerful technique designed to accelerate LLM inference. Instead of generating tokens one by one, where each new token requires a full forward pass through the large model, a smaller, faster draft model generates several candidate tokens ahead of time. The main, larger model then takes these speculative tokens and verifies them in parallel. If they're correct, it accepts them, effectively generating multiple tokens in one step rather than just one. The MTP layer, being a MoE layer itself, likely acts as the sufficient draft model or assists in generating these candidate tokens quickly and accurately. By predicting multiple tokens at once, it allows the larger model to work more efficiently, leading to significantly faster overall generation times during inference.
Now let's look at the parameter efficiency in detail, because Table 1 in their paper really lays out the architectural differences and tells a compelling story. GLM-4.5 has 355 billion total parameters, but only 32 billion activated. GLM-4.5 Air is 106 billion total with 12 billion activated. Compare this to, say, DeepSeek V3, which has 671 billion total and 37 billion activated, or Kimi K2 with a massive 143 billion total but a similar 32 billion activated. What does this comparative analysis tell us about GLM 4.5's design philosophy and its practical implications?
It highlights GLM 4.5's impressive parameter efficiency and its smart design choices. While Kimi K2, for instance, has a similar activated parameter count to GLM 4.5, both at 32 billion, its total parameter count is nearly 3 times higher. DeepSeek V3 also has both more total and activated parameters. The key takeaway is that GLM 4.5 manages to achieve strong competitive performance with a relatively smaller active parameter count and a significantly smaller total parameter count compared to these other leading models. This indicates that their architectural choices, particularly the depth over width approach, the optimized MoE configurations, and perhaps the specific training data methodologies, are leading to a very effective utilization of parameters. It's about intelligent design enabling high performance with a considerably reduced overall computational footprint during inference, which is a major advantage for practical deployment.
Which is incredibly important for real-world deployment, especially for open-source models where resource constraints can be a major factor. Now let's talk about the training process itself. It's described as a sophisticated multi-stage approach. First, the pre-training corpus. They mentioned 23 trillion tokens. That's a staggering amount of data. But quantity alone isn't enough, is it?
It is indeed a mind-boggling scale, but you're right, the sheer quantity is only one part of the equation. The selectivity and deliberate diversity of the sources are equally, if not more, important. They pull from a vast array of sources, including web pages, social media, books, academic papers, and code repositories. It's not just about collecting everything, it's about the strategic curation of that data to imbue the model with diverse knowledge and capabilities.
And they have quite detailed data processing pipelines. For web data, they categorize web pages into quality score buckets, ranging from very high to lower quality, and they upsample high-quality content, giving it over 3.2 epochs during pre-training, meaning the model sees this high-quality data more frequently. How does this strategy, emphasizing high-frequency knowledge, improve both reasoning and long-tail world knowledge? It seems like a delicate balance.
It's a very smart and precise approach to data weighting. By heavily upsampling high-quality content, which typically contains more factual, well-structured, and coherent text, they ensure the model is repeatedly exposed to the kind of information crucial for building robust reasoning capabilities and understanding high-frequency core concepts. Simultaneously, by including lower quality but still relevant data in the broader corpus, they aim to cover long-tail world knowledge, less common facts, niche topics, or diverse expressions, without diluting the model's focus on high-quality information during its most intensive learning phases. This allows for both deep understanding of core subjects and broad coverage of the world.
Right, and they tackle data duplication, too.
Yes, the challenge of data hygiene in such massive datasets is evident here. They use SemDedup, a method beyond traditional minhash, to remove automatically generated similar web pages. This technical detail reflects the real-world problem of large datasets being polluted by repetitive, templated, low-value content, and their commitment to cleaning it up for better training.
So it's about precision in data curation, not just volume. And for multilingual support, they include documents from crawled web pages and FineWeb 2, applying a quality classifier to judge what they call educational utility. That's an interesting term. What exactly does educational utility mean in this context for a large language model?
In this context, educational utility implies a focus on documents that are structured, informative, and contribute meaningfully to a model's understanding of facts, concepts, and linguistic nuances, rather than just casual conversation, entertainment, or low-value chatter. It's essentially a sophisticated filter to ensure the multilingual data is of high quality for deep learning, providing valuable signal rather than noise.
Okay, makes sense. And for code data, equally meticulous.
Absolutely. Rule-based filtering, language-specific quality models categorizing code into 3 tiers, and upsampling high-quality code. And crucially, they apply the fill-in-the-middle FIM training objective to all source code data.
Right. FIM. What is FIM and what's its distinct benefit for training models for advanced coding skills?
FI is a training objective where, instead of just predicting the next token in a sequence, the model is trained to predict missing segments of code given the surrounding context, both before and after the gap. This directly simulates real-world coding tasks like auto-completion in an IDE, refactoring, or even debugging, where a developer might need to fill in a missing part of a function or a logical block. Its immense benefit for code models is that it forces the model to develop a deeper bidirectional understanding of code structure, dependencies, and logical flow. This makes it far more proficient at generating coherent and syntactically correct code, as well as understanding and completing existing code bases rather than just churning out isolated lines.
That's a critical point for a model aiming for advanced coding skills, mirroring how human developers actually work. They also use a two-stage retrieval process for code-related web documents and a fine-grained parser to preserve code formats, which is vital for code readability and integrity. And for math and science data, they collect from diverse sources, use an LLM to score documents based on their educational content, then train a small classifier, upsampling documents above a certain threshold. This highly structured and multi-layered approach to data curation seems to be a conscious and deliberate strategy for knowledge acquisition across different domains.
It definitely is, and the pre-training process itself is two-staged, as illustrated in Figure 3 of their paper. The first stage focuses on general documents from web pages, forming a broad linguistic foundation. The second stage then strategically upsamples source code, math, and science-related web pages, allowing the model to deepen its domain-specific knowledge. This indicates a very intentional progression in building the model's capabilities, moving from general understanding to specialized expertise.
Precisely. Moving into mid-training, after this extensive pre-training, these are additional, more specialized stages that use medium-sized, domain-specific datasets, including initial instruction data. This is where they really start to boost performance in important application areas, going beyond raw knowledge to applying it. For repo-level code training, they take a very practical approach, concatenating code files from the same repository to learn crucial cross-file dependencies. This is absolutely vital for software engineering, as code rarely exists in isolation. Functions call other functions across files, and understanding that ecosystem is key.
Exactly, and they even include model-filtered issues, pull requests, PRs, and commits from GitHub in a diff-like format. That's incredibly practical and reflects real-world software development workflows, showing not just final code, but how code changes over time. They also extend the training sequence length from 4K to 32K here to incorporate large repositories, which makes sense given the scale of modern software projects.
Anyone who's ever jumped into a new code base knows that isolated files are a fantasy. It's like expecting to understand a novel by reading only isolated sentences. You need the whole narrative context. So learning cross-file dependencies is a huge step towards true software intelligence.
Yes, incorporating diff-like formats helps the model understand code changes, which is a key skill for a coding agent. For synthetic wrangling data training, they go a step further than just collecting questions and answers for math, science, and coding competitions. They emphasize synthesizing reasoning processes with a reasoning model. This is a key technical method for boosting pure reasoning ability.
So they're not just giving it the answer. They're essentially giving it the steps to get to the answer, even if those steps are synthetically generated by another AI. That's like teaching a student how to think through a problem, not just what to memorize. And for long context and agent training, they dramatically extend the training sequence length even further, from 32K to a massive 128K. And they upsample long documents and incorporate large-scale synthetic agent trajectories. Why is this dramatic increase in context length and the inclusion of synthetic agent trajectories so vital specifically for agentic capabilities?
That's an excellent question, and it goes to the heart of what makes agents effective. Agentic tasks often involve prolonged interactions, maintaining historical context, and the ability to process large amounts of information from the environment, whether that's long user queries, extensive tool outputs, or comprehensive documentation. Extending the sequence length allows the model to remember and process far more of the interaction history, previous tool outputs, and environmental observations without losing track. Incorporating synthetic agent trajectories is vital because it provides the model with thousands, if not millions, of examples of successful multi-step interactions with tools and environments. This teaches it how to plan, execute, and respond to feedback within complex multi-turn scenarios. It's essentially how the model learns to effectively act and strategize in a simulated environment before tackling the messy real world.
That makes perfect sense. The longer the memory, the more complex the tasks an agent can handle. To manage these changing sequence lengths efficiently, they keep it at 4,096 tokens in pre-training, then expand it to 32,768 and 131,072 in mid-training. And they note a distinction. No best fit packing in pre-training, citing random truncation as data augmentation, but applying it in mid-training to avoid truncating crucial reasoning or code. What's the thinking behind this dynamic approach to sequence length packing?
This highlights a crucial design choice tailored to the specific training phase. In pre-training, where the goal is broad language understanding from a vast, diverse text corpus, random truncation can actually act as a beneficial form of data augmentation. It forces the model to learn from incomplete contexts, making it more robust and better at generalizing. However, in mid-training, when dealing with highly specialized data like long reasoning chains or entire code repositories, truncating the context could sever critical dependencies, break logical steps, or cut off essential code blocks. This would effectively destroy the value of that specific data for training those capabilities. So best fit packing ensures that these coherent long sequences are preserved intact, which is absolutely essential for training the specific capabilities they are targeting in these later stages. It's about optimizing the data's utility for the learning goal.
And a crucial technical detail for long context modeling. They adjusted ROPI's base frequency from 10,000 to 1,000,000 when extending sequence length to 32K. Why is that specific adjustment so important, and what would happen if they didn't make it?
ROPE, or rotary position embedding, is designed to encode relative positional information, which is critical for how a transformer understands the order and relationships of tokens. Its base frequency directly influences how positional information is encoded across different distances within the sequence. When you dramatically increase the maximum sequence length, say from 4K to 32K, the model needs to handle much larger positional distances between tokens. Adjusting the base frequency allows the ropey embeddings to scale more effectively to these significantly longer contexts. Without this adjustment, the positional embeddings might become too granular or too coarse, degrading the model's ability to accurately grasp relationships between tokens that are far apart in an extended sequence. It's a fine-tuning of the positional encoding to match the vastly expanded contextual window, ensuring long-range dependencies can still be properly learned and utilized.
That's a deep dive into the underlying math that ensures long-term memory works. Now, for hyperparameters, they use the muon optimizer for most parameters, claiming it accelerates convergence and tolerates larger batch sizes. And they used a cosine decay schedule for the learning rate instead of a warm-up stable decay, WSB schedule, explicitly stating that WSD showed underfitting. These are very specific empirical choices. What do these tell us about their training philosophy?
Yes, the choice of optimizer and learning rate schedule are fundamental to efficient and effective training, especially at this scale. Muon Optimizer's ability to accelerate convergence and handle larger batch sizes suggests it's helping them push the boundaries of training speed and scale, optimizing resource utilization. Their decision to move away from the WSD schedule due to observed underfitting is highly indicative of a meticulous empirical approach to training. They aren't blindly following best practices, they're rigorously testing and adapting their strategy based on direct observation of model performance and learning dynamics, prioritizing strong generalization over a potentially more stable but ultimately underperforming training phase.
And they also did things like batch size warm-up.
Right, gradually increasing from 16M to 64M tokens, and specific settings for loss rebalance routing, and an auxiliary sequence level balance loss, plus an MTP loss weight adjustment. These granular details demonstrate a highly engineered, data-driven training process.
Moving on to post-training, which they describe as iterative refinement and specialization. It's a two-stage process. First, expert training, creating specialized models for reasoning, agent, and general chat domains. And then unified training integrates these multiple experts using self-distillation techniques to create a comprehensive model capable of generating responses through both deliberative reasoning and direct response modes. This sounds like an orchestra coming together after its musicians have individually mastered their instruments.
It's a very sophisticated and intelligent approach to building a generalist. Supervised fine-tuning, or SFT, is the initial polish here. In the expert training stage, SFT provides a crucial cold start with basic capabilities for each domain before more complex reinforcement learning kicks in. Then, in the unified training stage, its purpose is to distill the distinct capabilities of these different expert models into one cohesive, hybrid reasoning generalist. They use chain-of-thought responses and cold start SFT to build that foundational ability to show its work.
And in overall SFT, they train on millions of samples, covering diverse tasks from the expert models. A critical balance they mention is training data with full reasoning, with data lacking explicit thought processes, to enable hybrid reflective and immediate response modes. So the model isn't always showing its work. It learns when to just give a direct answer. How do they achieve that balance, and what's the significance?
Precisely. This balance is absolutely key to achieving that desired hybrid reasoning ability and making the model truly adaptable. For tasks that profoundly benefit from a deep, multi-step thought process, they provide training data with explicit chain-of-thought demonstrations. This teaches the model how to reason. But for simpler tasks, or when a direct, concise answer is preferred, they include data without that detailed to-do. This teaches the model to intelligently discriminate and dynamically choose the appropriate response mode based on the context and complexity of the query. The significance is that it makes the model far more efficient and natural for various interactions, avoiding unnecessary verbose outputs while still being capable of deep reasoning when required.
A major agentic challenge they highlight is the problem of character escaping for code segments within JSON function parameters, which significantly increases the learning burden for models. The proposed solution is a novel function called template, using XML-like special token tags to encapsulate keys and values. How does this clever design substantially reduce the necessity for character escaping, allowing for more native code representation? And could you walk us through the example provided in Figure 4?
This is a brilliant example of how a seemingly small design choice can have a massive impact on model performance and training efficiency. When code is embedded directly into standard JSON, every special character within that code, like double quotes, backslashes, new lines, etc., needs to be escaped. This makes a JSON string very long, incredibly difficult for humans to read, and, more importantly, adds significant noise and complexity for the model to learn and parse correctly. It's like trying to read a sentence where every single punctuation mark and special character is explicitly spelled out.
Right, it becomes unreadable noise.
Exactly. By using XML-like tags, such as argkey and argvalue, they create clear, unambiguous delimiters for the code segments. The model can then parse the content between these tags as raw code without the need for extensive character escaping. This dramatically simplifies the input format for the model, reducing that learning burden and allowing the model to represent and process code much more natively and accurately.
Okay, let's look at Figure 4, the weather example.
Right, the getWeather example clearly illustrates this. The system prompt defines the tool. The user query is simple: what's the weather like in Beijing? The model then enters its thinking process, deciding to call the getWeather tool. And here's where the new template shines. Instead of a messy JSON string with escaped quotes for Beijing and degrees Celsius, you see clearly delineated XML-like tags like location Beijing location and unit degrees Celsius unit. This clean, structured input allows the model to easily identify and parse the arguments for its tool call. The subsequent observation, the tool's output, and the assistant's final concise response flow naturally. It's a concrete example of improved agent interaction and significantly enhanced robustness.
That makes the interaction much cleaner for the model to learn and execute. For SFT data preparation, they also use rejection sampling with a multi-stage filtering pipeline to remove low-quality or incorrectly formatted samples. And they even use reward models for subjective questions. That's a robust approach to ensuring data quality.
It truly shows a strong commitment to meticulous data quality, understanding that garbage in leads to garbage out. They also applied strategies like filtering challenging prompts and performing response-level scaling. They found that removing the bottom 50% of prompts by response length, despite using half the data, led to a 2–4% improvement in math and science. And generating 4 responses for each hard prompt brought an additional 1–2% gain. This is quite an insight into optimizing SFT data efficiency. It's not just about raw quantity. Targeted quality and augmentation can be more effective.
So quality and targeted augmentation over sheer quantity. And they have an automatic agentic SFT data construction process with 4 steps, including generating tasks and trajectories with LLMs as user simulators and using multiple judge agents for quality filtering. That's a lot of automated data generation and curation happening, essentially leveraging AI to train other AIs.
It's a testament to how advanced LLMs themselves are being used to generate high-quality training data for other LLMs, creating a powerful, self-improving feedback loop. Now let's talk about Reasoning RL, which focuses on sharpening the model's mind in logical deduction, structured problem solving, and verifiable accuracy, particularly in domains like math, code generation, and scientific reasoning. The key here is high-precision reward signals, because correctness can be determined programmatically or with objective clarity.
That sounds like a powerful advantage for reinforcement learning.
Oh.
It gives clear feedback. What's the overall RL algorithm they're building upon?
They build upon the GRPO framework, specifically excluding the KO loss term. GRPO, or Generative Replay Policy Optimization, is a sophisticated reinforcement learning approach that essentially learns by replaying past successful or sometimes unsuccessful experiences. Think of it much like a coach reviewing game footage with a team to identify what worked and what didn't, using that feedback to improve their strategy. By excluding the KL loss term, they're likely fine-tuning the balance between sticking to known good strategies and exploring new ones, potentially making the learning more aggressive or stable for their specific tasks.
Okay, and they use a specialized technique, difficulty-based curriculum learning. The problem with static training data in RL is that it becomes less effective as the model learns. If tasks are too simple, all rewards are ones. If too difficult, all rewards are zeros. Both scenarios lack a useful gradient signal for learning. Their two-stage difficulty-based curriculum for RL, shown in Figure 5, enables the model to consistently surpass its performance ceiling. How does this two-stage approach work, and why are verified correct answers crucial here?
In the first stage, the model trains on moderately difficult problems, allowing it to build foundational reasoning abilities without being overwhelmed. Once it plateaus on this easier set, the second stage dynamically introduces extremely difficult problems. But crucially, all these extremely challenging problems come from a pool with verified correct answers. This ensures that even when facing very hard tasks, the reward signal remains precise and reliable, providing the necessary gradient for the model to learn and improve. Without verified answers for these difficult problems, the model could easily get lost, learn incorrect reasoning patterns, or receive noisy, useless gradients. This methodical, quality-controlled increase in difficulty, coupled with high-quality ground truth, is precisely what allows them to continuously push the model's performance ceiling.
That's a crucial distinction for robust training. Another counterintuitive finding for RL, they discovered the single-stage RL at 64K output length is actually more effective than multi-stage RL with progressively increasing lengths. Why is progressive increase, which often seems intuitive, less effective here? They mentioned shorter RL stages can cause unlearning of long context capabilities, leading to irreversible performance drops as seen in Figure 6.
This highlights a fascinating and sometimes frustrating challenge in training these massive, multi-capable models. If the initial SFT has already exposed the model to generating long, coherent responses up to, say, 64K length, then introducing subsequent RL stages with shorter maximum lengths, even if temporary for specific tasks, can inadvertently cause the model to forget or deprioritize its long context understanding. It essentially unlearns the behavior of generating long, coherent outputs because the reward structure of the shorter stages implicitly encourages brevity. Once that valuable capacity to handle extended context is diminished, it's difficult to recover in later stages, severely limiting the model's ultimate performance at its full intended context length. So directly training at the maximum desired length once the foundational SFT has established that capacity appears to be the more effective strategy for long context retention.
It clearly shows the delicate balance of capability retention during multi-stage training. They also use dynamic sampling temperature. The problem with a fixed sampling temperature is that it's either too convergent, leading to repetitive outputs, or too noisy, leading to incoherent ones. Their solution is to dynamically adjust temperature, and they have a quality control mechanism to prevent excessive noise. How does that sophisticated mechanism work to maintain balance?
When the average reward of rollout stabilizes, indicating the model is converging well on its current learning phase, they increase the sampling temperature. This encourages greater exploration and diversity in the generated outputs, preventing the model from getting stuck in local optima. However, to prevent this increased exploration from leading to excessive noise or low-quality responses, the quality control mechanism comes into play. They periodically evaluate the model's performance on a held-out validation set across a range of temperatures. They then set the temperature for the next training phase to the maximum value that does not cause a performance drop of more than 1% from the current optimum. This ensures exploration without sacrificing core quality, constantly pushing the model to generate better, more diverse, yet accurate outputs.
That's a clever and essential way to balance the trade-off between exploration and exploitation in RL. For Code and Science RL, they found token-weighted mean loss, Figure 7 left, to be critical for Code RL. This provides a finer-grained, more stable gradient signal, leading to faster convergence and alleviating length bias, which is a common problem in code generation where longer correct solutions might be penalized simply due to their length. And for Science RL, Figure 7, right, data quality and type are paramount. Training exclusively on small sets of high-quality, expert-verified multiple-choice questions yielded significantly better performance than mixed-quality data. This powerfully underscores the value of meticulously filtered RL data, especially in domains requiring high factual accuracy.
These insights into loss calculation and the absolute necessity of data quality are incredibly important for anyone trying to push the boundaries of model capabilities in these specialized domains. It really shows how specific the optimizations need to be. It's far from a one-size-fits-all solution.
Indeed. Now on to Agentic RL. which focuses on enabling the model to interact effectively with the world. The objective verifiability of web search and code generation tasks, where actions and answers can be automatically checked for correctness, provides dense, reliable rewards, enabling scalable RL training. This is a game changer for agentic tasks, isn't it, compared to subjective human feedback?
It absolutely is a game changer. Unlike general chat, where reward signals might be subjective and require expensive human annotation, agentic tasks provide clear, objective pass-fail criteria. If the web search agent successfully finds the correct answer, or the coding agent fixes the bug and passes all the unit tests, that's a direct, unambiguous reward of 1. This allows for far more efficient and scalable RL training because you don't need human annotators for every single interaction, enabling rapid iteration and massive data generation.
And how do they get the data for these tasks?
For data collection, they generate demanding Q&A pairs for web search tasks, using multi-hop reasoning over knowledge graphs and human-in-the-loop obfuscation to create realistic scenarios. And for software engineering tasks, they curate real GitHub pull requests and issues, with evaluations running in a hardened sandbox with a distributed system.
That's a highly realistic and robust evaluation environment, almost like a virtual software engineering firm. They also adopt group-wise policy optimization for RL training, and they use an iterative self-distillation approach.
Yeah.
RL train on an initial cold start model, then substitute original data with RL trained model responses to create a superior SFT model, and then further RL training with increasing difficulty. This sounds like a bootstrap method for continually improving performance.
It's an incredibly efficient way to continually push performance limits, especially since agentic RL can be very time-consuming. This self-distillation allows them to leverage the gains from RL training to generate higher quality data for subsequent supervised fine-tuning. This new RL-informed SFT model can then serve as an even stronger starting point for further RL iterations, creating a virtuous cycle of improvement. It's about maximizing the utility of every training step and scaling performance gains.
Smart. And they apply a crucial process format penalty for agentic tasks. If the model fails to produce the correct tool format, the process is halted, and it receives 0 reward. This is absolutely crucial for robustness in agentic tasks, enforcing precise tool interaction.
That penalty sounds like a tough but absolutely necessary teacher for an AI interacting with complex systems.
Definitely. And Figure 8 strikingly shows how agent tasks leverage test time compute via interaction turns, leading to significant performance gains with more interaction turns. So the more chances the AI gets to interact with its environment, the better it performs.
Yes, that's a fundamental difference in how agentic models scale compared to traditional reasoning models. Unlike reasoning models that primarily scale by generating more output tokens internally, agents scale by interacting with an external environment. Whether it's iterating on a search query, running multiple test cases for self-correction and coding, or trying different tool calls based on feedback, each interaction turn offers new information and opportunities for refinement. This allows the model to dynamically think and adapt based on real-time feedback, leading to substantial gains in accuracy as it leverages more test time compute through these interactions. It's like an intern learning on the job. The more practical experience, the better.
That's a powerful insight into how agentic models fundamentally differ in their scaling. Moving to general RL, the goals here are holistic performance improvement, targeted remediation of persistent issues like language mixing or repetition, and strengthening key capabilities across the board. They use a multi-source feedback system, synergizing rule-based feedback, human feedback, RLHF, and model-based feedback, RLAIF. What's the core benefit of combining these diverse feedback sources?
Combining these different feedback sources provides a far more robust, comprehensive, and scalable training signal. Rule-based feedback offers precision and consistency for clearly defined behaviors and hard constraints. Human feedback, RLAF, captures nuanced judgments, subjective preferences, and safety considerations that are difficult to codify. Model-based feedback, RLAAF, provides scalability by leveraging other advanced LLMs to evaluate responses, allowing for massive amounts of data generation without relying solely on human annotators. This hybrid approach effectively mitigates the limitations of any single source, leading to more reliable and expressive reward signals and a better-rounded, more adaptable model.
And for holistic RL, they use an incredibly balanced data set.
Yes. 5,000 prompts across 7 primary, 33 secondary, and 139 tertiary categories.
That's an extremely fine-grained categorization. It really shows the effort to ensure comprehensive coverage and prevent any particular domain from dominating the training. For instruction following RL, they use an even finer grained taxonomy, 7 major and 151 minor constraint types, with a dedicated training set of challenging instructions. And they observe something called mitigated reward hacking and continuous improvement, as seen in Figure 9. What exactly is reward hacking in this context, and how do they manage to mitigate it so effectively?
Reward hacking occurs when a model learns to exploit flaws or loopholes in the reward function to maximize its score, rather than actually performing the desired behavior or following the instruction correctly. For instance, it might generate repetitive outputs, superficial responses, or outputs that coincidentally align with a simple reward signal without truly understanding or fulfilling the instruction. They mitigated this through a sophisticated hybrid feedback system, combining deterministic verification rules, a train reward model, and a critique model. The deterministic rules provide hard boundaries, preventing the model from generating malformed or obviously incorrect outputs that might otherwise fool a less strict reward model. The critique model, likely another LLM trained to spot subtle deviations or forms of cheating, provides more nuanced feedback. This multi-layered approach makes it significantly harder for the model to find loopholes and forces it to genuinely improve its instruction-following capabilities, resulting in more reliable and robust behavior.
So it's about making the reward signal as robust and unhackable as possible. Now, function calling RL is divided into stepwise rule-based RL and end-to-end multi-turn RL. For stepwise, they use an incredibly strict reward function. Reward one only if format correct and match at, meaning name, parameters, and every field must be perfectly correct. Otherwise, zero. Why such an unforgiving reward? It sounds brutal.
This strict reward function is designed to enforce extreme precision in function call formatting, and brutal is perhaps the right word for its stringency. In real-world agentic scenarios, even a tiny formatting error, a misplaced comma, a wrong bracket, or an incorrect parameter name can cause a tool call to fail entirely. There's no room for almost right. By penalizing any deviation from the ground truth format with a zero reward, they compel the model to learn to generate perfectly formatted function calls with extremely high reliability. This significantly improves the model's usability and robustness in practical deployment, where consistent and correct tool invocation is paramount for successful task completion. It's tough love for a critical skill.
That strictness is key for practical deployment, ensuring the model is truly reliable. And for end-to-end multi-turn RL, the model generates a complete trajectory and is rewarded based on overall task completion. This allows optimization of action policy through continuous trial and error with tool feedback, enhancing autonomous planning and decision-making. What types of complex tasks are they considering here to push these capabilities?
They consider two main types of complex tasks. First, single-turn, multi-step tasks, where the model needs to make multiple function calls and interact with the environment within a single user turn. Examples include complex tasks synthesized based on environments like Minecraft Protocol, MCP servers, and open-source agentic datasets like Agentic. Second, and arguably more complex, are multi-turn, multi-step tasks. Here, the model interacts not just with the tool execution environment, but also with an LLM-simulated user agent to obtain complete task information and accomplish the overall task over a longer dialogue. This pushes the model's ability to plan, adapt, and refine its strategy over extended conversations and more complex, evolving scenarios, truly aiming for autonomous problem solving.
That's truly aiming for autonomous problem solving, moving from single actions to full complex projects. And finally, Pathology RL aims to rectify low-incidence pathological behaviors like language mixing, repetition, or specific formatting mistakes. They curate a targeted dataset specifically for this. Why is this specific focus necessary, given that they have general RL stages already covering a broad range of behaviors?
That's a great question, and it speaks to the limitations of general training. Even with broad general RL, these pathological behaviors, while rare in the overall dataset, can be very disruptive to the user experience. Their low incidence rate means a general reward function won't provide frequent enough or strong enough gradient signals to efficiently eliminate them from the model's behavior. It's like trying to fix a very specific rare bug by just running a general stress test. You might not hit it often enough. By creating a targeted dataset of prompts that are highly likely to trigger these specific pathologies, they can efficiently impose strong penalties when they occur. This concentrated training allows them to significantly lower the residual error rates for these problematic behaviors, leading to a much more reliable and polished model for end users. It's a focused strike against specific, annoying weaknesses.
So, a surgical strike against specific flaws. Now let's talk about the engine behind all this complex training. Their open-source RL framework called Slime. It features a flexible hybrid training and data generation architecture supporting both a co-located synchronous mode and a disaggregated asynchronous mode, as seen in Figure 10. What's the practical difference between these modes, and why is this flexibility absolutely crucial for training such a generalist model?
The co-located synchronous mode is where the training and inference engines reside on the same worker, meaning data generation and model updates happen in lockstep. This is highly efficient for general RL tasks or reasoning, as it minimizes GPU idle time and communication overhead. However, for agentic tasks like software engineering, where data generation involves protracted and complex system interactions, think waiting for a simulated environment to compile code, run tests, or interact with a complex API. A synchronous setup would lead to significant delays and massive underutilization of expensive GPUs, essentially leaving them waiting idly.
That's where the disaggregated asynchronous mode comes in to save the day.
Exactly. In this mode, the rollout component, which generates data by interacting with the agent environment, is completely decoupled from the GPUs used for training and inference. The GPUs for training and inference are scheduled independently, allowing them to run continuously. This ensures that the agent environments can continuously generate new data without being stalled by the training cycle. This flexibility, leveraging frameworks like Ray, is absolutely crucial because it allows diverse RL tasks with their wildly varying interaction patterns and data generation requirements to share a common, optimized infrastructure without bottlenecks. It's like having a dedicated production line for data generation that feeds seamlessly into another dedicated line for model training, ensuring both are always busy.
That's a very smart way to handle the varying and often unpredictable demands of different RL tasks. And to further address rollout efficiency, which is often a bottleneck in RL training, they support BF16 for training, but leverage FP8 for inference, using dynamic online blockwise FP8 quantization. How does this mixed precision approach accelerate the data generation phase?
Inference is the part of the process where the model generates responses or takes actions in the environment, and it's typically the most frequent operation in RL training loops. BF16 provides a good balance of precision and speed for the actual training calculations, maintaining model accuracy. But FP8, with its even lower precision, allows for extremely fast computation during inference. By dynamically quantizing the model parameters to FP8 before dispatching for rollout, they significantly reduce the computational load per inference step. This directly translates to faster data generation, improving the overall throughput of the data collection process and allowing more training steps per unit of time. Simply put, faster rollouts mean more data, which means faster learning and a more efficient use of expensive GPU resources.
So faster rollouts mean more data, which one's faster learning. And their agent-oriented RL infra design also includes a high concurrency Docker-based runtime for isolated environments, which significantly reduces rollout overhead. Plus, a fully asynchronous RL training loop that smartly partitions GPUs into dedicated rollout and training engines to prevent underutilization, even with variable trajectory lengths.
This is all about maximizing hardware efficiency and robustness for complex agentic tasks. The Docker-based runtime ensures that each agentic task runs in its own isolated, reproducible environment, preventing interference between tasks and streamlining the setup teardown of environments, which can otherwise be a costly overhead. And by having dedicated rollout and training engines, they completely avoid the straggler problem. If one agent rollout is very long or complex, it won't block the entire training pipeline. Rollout engines continuously feed data, while training engines continuously update weights, ensuring high throughput and efficient GPU utilization, even with highly variable agent interactions.
And a unified HTTP endpoint interface with a centralized data pool decouples task-specific rollout logic from RL training, enabling seamless integration of heterogeneous agent frameworks. That sounds like a universal adapter for agents, making it easy to plug in new environments.
Exactly. It provides a standardized and flexible way for any agent framework to interact with the core RL infrastructure. Since most agent frameworks ultimately produce rollouts in a message list format, they can all funnel into this centralized data pool. This architecture cleanly separates the concerns. The RL training loop doesn't need to know the intricate specifics of how an agent generates its trajectory. It just pulls the process data from the pool. This is absolutely critical for scaling across a wide range of diverse agent tasks, allowing for customizable filtering and dynamic sampling, truly building a powerful, adaptable ecosystem for agent development.
That's an impressive infrastructure for such complex and varied training needs. Now let's turn to evaluation, which is where we truly see the rubber meet the road, and these innovations prove their worth. They have a comprehensive evaluation strategy, assessing base models, their core ARC benchmarks, general abilities, safety, and extensive human evaluations to truly reflect real-world experience. For the evaluation of base models, Table 2 shows GLM 4.5 base pre-instruction training demonstrates impressive stability across English, code, math, and Chinese benchmarks. This significantly validates their unifying all abilities idea even before fine-tuning. And it achieves this with only 32 billion activated parameters compared against competitors like DeepSeek V3 37B activated and Kimi K2 32B activated, while having significantly fewer total parameters than both.
This initial evaluation is crucial because it robustly demonstrates that the foundational pre-training has successfully instilled a broad range of capabilities before any instruction tuning or specialized post-training. The fact that it achieves comparable performance with fewer total parameters than DeepSeek V3 or Kimi K2 highlights the inherent efficiency and effectiveness of their MOE architecture and training methodology at a fundamental level. It's a strong testament to their efficient parameter utilization.
Moving on to the ARC benchmarks, which represent the core strengths they targeted. For agentic abilities, Figure 1, Table 3, GLM 4.5 scores 70.1% on TAU Edge, which breaks down to retail 79.7%, airline 60.4%, and 77.8% on BFCL v3. Crucially, on BrowseComp, a challenging web browsing benchmark, GLM 4.5 at 26.4% clearly outperforms even a leading closed-source model like Claude Opus 4, which scored 18.8%. Overall, GLM 4.5 ranks an impressive second on agentic task among all evaluated models, following only OpenAI's GPT-4. What does outperforming Claude Opus 4 on web browsing really signify for you, the listener?
That's an incredibly strong showing for interacting with the world, especially for an open-source model. To outperform a closed-source behemoth like Claude Opus 4 on web browsing is a massive achievement. It means GLM 4.5 isn't just generating text, it's effectively navigating the internet, understanding complex web pages, interacting with forums, and extracting specific information to fulfill requests, a crucial skill for any AI that needs to operate in the messy, unstructured, real world. Think of the implications for automated research, customer service, or data collection.
And that TAU bench example in Figure 11 really shows it.
Exactly. It gives a clear illustration of the complex multi-turn interactions and constraint handling these models are now capable of, which is essentially bringing the AI closer to behaving like a human assistant using a computer.
For reasoning abilities, Figure 1, Table 4, we see outstanding performance on some incredibly tough benchmarks. AIM 24, 91.0%, GPQA 79.1%, Live Code Bench 72.9%, and HLE 14.4%. Notably, GLM 4.5 outperforms OpenAI GPT-4 on AIM-24 and Scicode. On average, it outperforms Claude Opus 4 and is very close to DeepSeek R1 now 0528. This really demonstrates its prowess in deep logical deduction, a cornerstone of intelligence.
These are indeed highly challenging benchmarks, specifically designed to test true reasoning, not just recall. AIM is an American invitational mathematics examination akin to a high school math Olympiad, and GTQA is designed to be Google-proof, requiring deep scientific understanding and multi-step reasoning. Achieving such high scores on these benchmarks and even outperforming a top-tier proprietary model like GPT-4 on certain reasoning tasks powerfully underscores the effectiveness of their architectural choices and their sophisticated multi-stage reasoning training, especially the curriculum learning and meticulous data curation we discussed earlier. It means the model isn't just mimicking, it's genuinely processing information and deriving solutions.
For coding abilities, Figure 1, Table 5, GLM 4.5 scores 64.2% on SWE Bench Verified and 37.5% on Terminal Bench. It outperforms GPT 4.1 and Gemini 2.5 Pro on SW Bench Verified and outperforms Claude Sonnet 4 on Terminal Bench. On average, it's the best competitor for Claude Sonnet 4 on coding tasks. These aren't theoretical coding puzzles. These are real-world software engineering tasks, so this is very significant.
It is indeed, and it's a truly impressive result for real-world software engineering tasks. SW Bench involves resolving actual GitHub issues by modifying existing code bases, which is a complex multi-step process requiring deep understanding of context, debugging, and often multi-file changes. Terminal Bench requires interaction within a terminal environment to complete tasks. Excelling in these benchmarks means the model isn't just generating synthetic code snippets, it has developed practical software engineering capabilities that are directly applicable to development workflows. The performance against leading proprietary models like GPT 4.1 and Gemini 2.5 Pro is particularly noteworthy for an open-source offering, marking it as a strong contender for various developer tools.
Moving to general abilities, Table 6, GLM 4.5 shows highly competitive performance across a range of benchmarks, including MMLU, Massive Multitask Language Understanding, Simple QA, IFEVL, Instruction Following Evaluation, SysBench, and Multi-Challenge. And it further highlights its parameter efficiency on Simple QA, where it performs similarly to models with nearly double its parameters. It also outperforms GPT 4.1, DeepSeek V3, and Kimi K2 on Sysbench, and GPT 4.1, DeepSeek R1 on multi-challenge. So it's not just specialized in ARC, it's a generally very capable and well-rounded model.
This is absolutely critical for validating its claim as a generalist model. It confirms that their targeted optimizations for agentic reasoning and coding capabilities haven't come at the expense of general knowledge, instruction following, or overall conversational prowess. The parameter efficiency on simple QA in particular is a strong indicator of effective architecture and training, making it a more practical choice for deployment in scenarios where both broad capability and resource efficiency are important. It's a versatile powerhouse.
For safety evaluation, Table 7, they utilize Safety Bench, an extensive benchmark comprising 11,435 multiple-choice questions across 7 different safety categories. GLM 4.5 achieved a strong overall score of 89.87%, putting it in direct competition with Kimi K2, 90.48%, and GPT 4.1, 89.71%. With specific strengths in ethics and morality, 94.33%, mental health, 94.67%, and physical health, 96.67%. While acknowledging some room for improvement in unfairness and bias, this shows a clear commitment to responsible development.
It's good to see such a strong emphasis on safety from the outset, especially as these models become more capable and are deployed in diverse real-world applications. A high safety score indicates a model that is less likely to generate harmful, biased, or unethical content, which is paramount for public trust and practical utility.
Now, on to the hands-on experience. Human evaluations for real-world performance. They acknowledge that models can sometimes overfit benchmarks, so they use meticulous manual evaluation for open-ended questions and qualitative analysis to capture real-world usability. For general chat, tables 8, 9, 10, GLM 4.5 achieved the highest overall scores in English, 8.66, Chinese, 8.37, and other languages, 8.49, showing consistent strengths across categories like math, objective QA, text generation, logical reasoning, and code instructions across multiple languages. This strongly suggests robust real-world usability and fluency.
Human evaluations are invaluable because they capture nuances that automated benchmarks often miss, such as coherence, relevance, creativity, and overall naturalness of the conversation. The consistent top performance across multiple languages and diverse chat categories suggests GLM 4.5 is indeed a very capable and versatile generalist for real-world conversational applications, demonstrating a high degree of adaptability and understanding.
For Coding Agent, figures 12-13, they use CC Bench, a benchmark of 52 real-world programming tasks executed in isolated containerized environments, with human experts overseeing the evaluation. GLM 4.5 showed clear dominance over open-source baselines and was highly competitive against even closed-source models like Claude Sonnet 4, boasting a 40.4% win rate against it and an impressive 80.8% against Qwen 3 Coder. And its highest tool calling reliability at 90.6% is a key practical metric. What does that reliability tell us about its potential in software development workflows?
This is a truly impressive result for real-world software engineering tasks, and that high tool calling reliability is perhaps the most important takeaway. It tells us that when GLM 4.5 decides to use a tool, whether it's running a test, interacting with a file system, or calling an API, it does so correctly and reliably over 90% of the time. This consistency is fundamental for any AI agent meant to operate autonomously in complex environments. It means the model isn't just making educated guesses, it's reliably interacting with external systems, which is paramount for successful task completion and actual development workflows.
And it uses fewer tokens, too, according to figure 13.
Right. Its token usage efficiency is another practical advantage, indicating lower operational cost for these complex agentic tasks.
For logical reasoning, table 11, they constructed a new, challenging evaluation set with novel, complex problems specifically to mitigate any potential data contamination. GLM 4.5 scored 62.00, performing on par with leading models like Gemini 2.5 Pro, 65.8, and DeepSeek R1, 052 and 8, 62.1. This indicates genuine reasoning ability, not just memorization or recall from training data.
This is a strong validation of their dedicated focus on reasoning capabilities throughout the training process. Creating a novel data set specifically to avoid contamination from widely available problems ensures that the model's performance truly reflects its ability to reason and solve new, unseen problems, rather than simply having seen variations of them during training. It's a critical measure of true cognitive ability, demonstrating that GLM 4.5 has learned transferable reasoning skills.
And finally, translation, table 12. They describe a new paradigm of translation that goes far beyond literal text conversion, requiring nuanced understanding of internet slang, like yards meaning eternal God or greatest of all time, cultural context like using a fish emoji for Shanyu marketplace, domain-specific terminology like pang, meaning fat, being used as a specific lens name in Canon photography, and deep contextual reasoning for Calico Cat. GLM 4.5 significantly outperforms specialized translation models like QuintMT plus Turbo and SeedX with an average score of 1.71 out of 3. This is a powerful demonstration of a generalist model's strength in what has traditionally been a niche domain. What does this new paradigm really mean for how we think about translation, and why does GLM 4.5 excel here?
This is perhaps one of the most compelling examples of why the generalist approach is so powerful and why this is indeed a new paradigm. Traditional specialized translation models, while highly optimized for literal grammatical translation, often struggle with the subtle, culturally embedded meanings, slang, and domain-specific jargon that require broad world knowledge and deep reasoning. These are precisely the strengths of a generalist LLM like GLM 4.5. Its ability to accurately translate such nuanced expressions demonstrates its capacity to connect diverse knowledge domains, from internet culture to photography, and reason about context, which is a hallmark of true general intelligence. It means translation is no longer just about linguistics. It's about comprehensive understanding of human communication in all its messy, beautiful complexity.
So to recap our deep dive, the GLM 4.5 series, including GLM 4.5 and the more compact GLM 4.5 Air, represents a major open source advancement. Its innovative mixture of experts architecture and comprehensive multi-stage training have clearly paid off. We've seen its impressive, balanced performance across agentic, reasoning, and coding tasks, which positions it as a truly generalist model, scoring third overall among all evaluated models, both open source and proprietary.
Absolutely. The release of such a capable open source model, along with its extensive evaluation toolkit and underlying infrastructure like Slime, is a significant moment for the entire AI community. It not only provides a powerful, accessible tool for developers and researchers, but also significantly accelerates innovation across the broader field, fostering new applications and further research into these generalist capabilities.
And as we close this deep dive, here's a thought to mull over. Considering GLM 4.5's hybrid reasoning modes, the ability to intelligently choose between a deep, deliberate thinking process and an immediate direct response, how might this nuanced capability fundamentally reshape how we design and interact with AI for complex problem-solving in the real world? Could this flexibility pave the way for more intuitive and adaptable AI assistants in professional settings, allowing them to fluidly switch between complex analysis and quick, decisive action without explicit human instruction, becoming truly seamless partners?
It raises an important question about the future of human-AI collaboration. If an AI can intelligently decide when to think and when to act immediately, based on the problem's nature, it becomes a far more natural and efficient partner. The implications for workflow optimization and complex decision-making in fields ranging from engineering and scientific discovery to legal analysis and medical diagnostics are immense. It could lead to AI assistants that are not just smart, but truly wise in their approach.
Excellent. The potential for more intelligent, context-aware AI interactions is truly exciting. That's all the time we have for this deep dive into GLM 4.5. For more insights and the latest research papers in AI machine learning, visit our webpage, neuralintel.org. Thank you for joining us on this journey into the technical frontier of AI.